This last section in chapter 11 talks about water. We use water for all kinds of things, and so we don't necessarily appreciate how amazing and extraordinary it actually is. It's the most common and most important liquid on Earth. There are actually very few substances that are liquids at room temperature. Can you think of one besides water?
Mercury?
Mercury. Is mercury super common? Just, around? No, not very common. Can you think of any other liquids?
In our atmosphere?
Well, yeah, in liquids on our planet.
Naturally,
Well, not necessarily naturally occurring, but just liquids that you run into.
maybe lava of some sort.
Acetone is a liquid. Lava would, well, those are at really high temperatures. So think about like more room temperature. But lava is a liquid. Alcohol. How about vegetable oil? Vegetable oil? Olive oil, canola oil? Those are liquids. They're not pure compounds. They're unsaturated fats. Yes.
I think it's unsaturated.
Yeah, oils basically. And then another one would be like gasoline or motor oil, those sorts of things. But those are much smaller quantities. You think about how much water there is on the planet, the ocean. You guys did better than my Tuesday, Thursday class, actually, because they were telling me things like coffee. Well, yeah, coffee's a liquid, but what's the liquid in coffee? It's water. Soda's a liquid, but it's water with stuff in it, right? So points for you guys. Water has a low molar mass, and we learned that molar mass and strength of intermolecular forces are sometimes related. And so many of the things that have low molar masses are gases at room temperature. But water is a liquid, and that is because of hydrogen bonding. We'll look at a graph in a minute. It's the main solvent within living organisms. The blood in your body and all of the cellular fluids and all of those things have water as the solvent. Water has an exceptionally high specific heat capacity. It's 4.184 joules per gram degree Celsius. Metals are less than 1, and so because of that, water can moderate our climate. It helps to absorb the heat and then release it later when the temperature goes down. Another very unusual thing about water is that it expands upon freezing. Most things, when they become a solid, become less dense. They shrink. I'm sorry, I always get this backwards. Okay, start that over. Most substances, when they become a solid, they become smaller and more dense. Water does not. It actually expands, and that's the reason that ice floats. And here we have an example, ice floating in water. Because it's less dense, it expands. And that has implications for lots of things. That's why you have to protect your pipes from freezing in the winter, because when the water freezes, it expands, and it's amazingly powerful. I think most people have had an experience where you put like a bottle of Gatorade or a can of soda or something in the freezer to cool it down and forgot about it, right? You come back later and it's burst open, the container, because it expands when it freezes. The way to avoid that is make sure that there's a little bit of airspace in there so that the liquid can expand. But it is powerful enough to break metal pipes, even. It also does a number on living cells. So here's a head of lettuce. You freeze it, and it looks like that afterwards, because the water in each of the cells expands and bursts the cell membranes. And so that's why many plants are killed by a frost, because it breaks the cells. Any questions about that? We saw a simpler version of this graph when we were talking about boiling points and the relationship to intermolecular forces. Here we've got, these are all hydrides of main group elements. We've got group 4 and group 5 and group 7 and group 6. And if we ignore this first period, it's actually the second period here, if we just look at these, we see there's a general trend that as the element gets larger, that central atom, sulfur to selenium to tellurium, we see that the boiling point of the substance goes up. And that's because the intermolecular forces, mainly dispersion forces, get stronger as that molecule increases in size. But when we look at the period 2 elements, we see this huge discrepancy here. We would expect these to have boiling points down around, minus 100 or so, and yet ammonia, hydrogen fluoride, and water have much higher boiling points than would be predicted. And that's due to what? Hydrogen bonding. Remember ET phone home? So here's fluorine, oxygen, and nitrogen. Those are the 3 elements combined with hydrogen that can involve hydrogen bonding. So that causes water to have a much higher boiling point. If it weren't for hydrogen bonding, all the water on Earth would be in the gas state and things would be very, very different. Of course, water quality is very important. It's important for human health and for the health of the environment. I'm not going to test you on this, but I just want you to be aware there are 2 basic types of water pollution. There are biological contaminants and chemical contaminants. And it's important to recognize the difference because you would get rid of them in different ways. So biological contaminants are going to be microorganisms, and those can cause some pretty serious diseases. Those are commonly going to get into the drinking water when you've got animal or human waste that's dumped either into the body of water or too close. And so, when people get E. coli or something from like strawberries or lettuce or something, it's usually because there were cows upstream and from their cow pies, the toxins and viruses and stuff get into the water and they get into the fruit, onto the fruit. And then if you don't wash them correctly, you can get pretty sick. You can treat this sort of contamination either chemically or often by boiling the water. So usually if you boil the water, that'll kill most of the microorganisms. If you're camping and need to get water from a stream, you can get different sorts of chemical treatments. Iodine or bleach will kill many of those microorganisms. The other type of contamination is a chemical contaminant. These are not living organisms, and so they can't be killed by boiling. In fact, boiling can make it worse. If you have lead in your water that's leached out of your lead pipes, boiling the water is actually going to make it worse because some of the water will boil out and the remaining water will have a higher concentration of lead. So chemical contaminants require a little more effort to get rid of. And they're usually going to result from either industrial or household dumping, pesticide, fertilizer use. But you can have chemical contamination of water that is entirely naturally occurring. You can have groundwater, and if it's going through a type of rock that has lead or another type of, anything that would be toxic in it, it can leach into the water. And so you can have natural water that has chemical contamination. Any questions?